All right. The analysis we did previously is called PVT analysis, pressure, volume, temperature analysis. So the formation volume factor calculations, the RS plot, all these are called basically the PVT calculations. And this PVT analysis for this specific oil that we discussed there was defining the formation volume factor, right, in barrels per stock tank barrels. Important to understand. For that specific example that we did here, it was 1.31, right, barrels per stock tank barrel. This R is reservoir barrel. Bubble point pressure, the pressure at which there is no free gas above that pressure, right, as we discussed again in the PVT, pressure temperature diagram. And you see that the bubble point pressure changes with temperature, right? So this is called the bubble point line, and all those points on this curve up to the critical point are bubble point pressures at different temperatures, right, depending on what is the reservoir temperature. And we have solution gas oil ratio, which is shown with RS or GORS as well. The S represent the solution, means that the solution gas ratio that is we are talking about it. The unit is a standard cubic feet of gas per stock tank barrels of oil. It's basically the standard volume of gas that is dissolved in 1 stock tank barrels of gas oil. So some more parameters that are important is the specific weight and specific gravity. So specific weight is the weight per unit volume. And for water, for example, specific weight is 62.4 pound per cubic feet, which is, it's a density, right? Weight per volume is density. So that's basically the same thing here that we're talking about. Then we have a specific gravity, which is the ratio of specific weights or densities, any liquid with respect to water, right? Water is 62.4. Whatever liquid that you want to calculate, put it here. If you have the density, and then you can get the specific gravity. For example, a specific weight of a liquid is 52.7. What is its specific gravity? You just divide this number by 62.4. You get 0.845. It's a dimensionless number because it's the ratio of volumes, right? Some other parameter for basically density, or I would say the weight of fluids that we use in petroleum engineering, is called API gravity. And API, so you may, if you look at the papers or look at the industry reports of the fluid properties, you will see that API gravity is used, and API gravity is basically defined based on the specific gravity, and it's 141.5. This is a certain specific equation we use. 141.5 divided by specific gravity minus 131.5. So for example, for water, if you want to calculate the specific gravity, the API gravity, you just put 1 there because the specific gravity of water is 1, right? Gamma liquid again over gamma water is called specific gravity, right? So for water, if you use water, then it's 1. The ratio is 1. Put it there, you get 10, right? Oil, depending on how they are, they may be heavier or lighter. So the heavier oils have an API. The heavier the oil, the higher the specific gravity, and the higher the specific gravity, the lower this ratio, right? So and if the oil is very light, then you will have very high API values, basically because the specific gravity is low. You divide it by that, you get basically the API gravity, right? And in general, the density of the oil is lower than water, right? That's why the water have a 10 API gravity here, which is small, and that means it's heavy, right, compared to oil, of course. So another parameter in PVT analysis that are important is the viscosity. Viscosity is the resistance of that fluid to flow, and indicates that if you have a high viscosity fluid, then it means that the fluid really resists to flow, right? For example, compare honey to water, right? Honey have high viscosity. It doesn't really want to flow, right? But water can flow very easy, right? So water have lower viscosity than honey, right? Now viscosity of oil important because we want to produce from the reservoir, and we will have a flow inside those rocks at the underground, in the underground reservoirs, right? And viscosity of oils also is a function of pressure, and you can see that as the pressure drops above bubble point up to the bubble point, your viscosity drops, right? Well, one of the reasons for this that happens is that this is oil specifically, the liquid part we are talking about, right? So look at the oil, what happens at, let's say, 2 stages, and then we have bubble point stage, right? Bubble point pressure. So we have fully liquid here, right? And there are dissolved gas at a high pressure, let's say 3000 psi, right? Above bubble point pressure. And then let's say at 2700 psi, where the pressure has dropped inside the reservoir, then you have basically you have more oil, right? And let me draw it in another way, a little bit expanded, right? You still have oil, everything is still dissolved, but then you have larger bubbles because the pressure have dropped, but still you see that it's not released or evaporated, right? So the system is expanded, right? Your liquid is expanded, and therefore its viscosity drops because you see more volume of gas in it. Gas has very low viscosity, it can flow very easily, right? So if you have more volume of gas inside your fluid, then it means it's lower viscosity. So as the pressure drops above bubble point pressure, the viscosity drops because your oil expands, right? And then once you reach to the bubble point pressure, then this gas will be released, let's say at 2000 psi pressure. It's below, let's say your bubble point pressure was 2500 psi, right? At 2000, then you have some oil here, right? And then some free gas. This oil lost gas. It means that it's much heavier now, so it is very viscous, right? Further drop in pressure, more free gas. So again, heavier oil still here, even heavier than the 2000 psi because it lost some gas, right? So it's heavier. And the heavier the oil, the higher the viscosity. So you see that how exponentially your viscosity goes up as the pressure drops because your oil loses gas. Okay, so that's the concept basically, and typical values for a reservoir: 1.1 bubble point pressure, 2500 psi. A normal oil have a 36-degree API, gravity kind of on average, gas oil ratio, how much gas is dissolved, around 500-ish, and viscosity around 0.6 centipoise. Centipoise is, I forgot to mention, the unit of the viscosity, and the unit of the viscosity is actually Pascal second, pressure time. That's the unit of viscosity. And if we have a milli, means 10 to the negative 3 Pascal second. My pen is not working now. Okay, it's not working. So if you have 10 negative 3 Pascal second, which means this is a millipascal second, then in that case we call this unit centipoise. So centipoise is actually 10 to the negative 3 Pascal second. That's what it is. Anyway, that's the unit we use for viscosity, and I guess that's it for this video. We'll continue this topic, or maybe let's finish here. We have also a definition which is for solution and producing gas oil ratio. So solution oil gas ratio means that how much of this gas is dissolved inside the oil, as we discussed it previously. Producing gas oil ratio means how much gas we are producing. So they might be different. If the bottom hole pressure, which is shown with PWF, is greater than the bubble point pressure, which means that everything is coming out of your reservoir is liquid 100%, right? If this pressure is above the bubble point pressure, it means everything here is liquid. And in that case, the gas oil ratio is equal, the producing gas oil ratio is equal to solution gas ratio. Now, if you have a reservoir, that in that reservoir you have some oil and also you have some free gas, then whatever you are producing is both the gas is whatever gas you produce at the surface is the gas coming out of the oil as well as the free gas, and that is called producing gas oil ratio. So if your pressure is at the bottom hole is less than bubble point pressure, PB, right? Then in that case, the GOR producing is higher than the GOR solution, and the reason is that you have some solution gas, some free gas also being produced, right? Actually, it's in this slide. So I guess that's it for this video. I'm gonna continue in the next video.